Good morning, all of you. Today we will continue our discussion on plasma etching, which is dry process in VLSI. In a plasma process, the main issues are etch directionality, etch selectivity, plasma diagnostics and process control, plasma induced damages. Etch directionality an important issue because it will give you some idea about the etch quality, rather whether the etch is isotropic or anisotropic. Etch selectivity already have discussed in detail. Selectivity is very important point, so that you can etch only your desired film to be etched, and others means mask and substrate should not be etched. So that give you etch selectivity. And the third one is plasma diagnostics and process control. You are creating a plasma, and that plasma, how much will be the density of the plasma, what should be the pressure inside the plasma chamber, how it should react with etch materials. All those parameters depends on the plasma diagnostics and process control. And the process control parameters separately I will discuss in a different slide. And the third one is plasma induced damages. This is an important concern in dry processing, which is not there at all in case of wet processing, because you are creating a plasma, and plasma is a combination of charged particles as well as some neutral atoms and ions. Okay, charged particles, electrons, and positive and negatively charged ions will be there, and at the same time some neutral atoms and as well as the fragments of elements are also there. The combination of all those materials constitute a plasma. And also that in a plasma there are two electrodes, and the electrons and ions, they will accelerate inside the plasma chamber, and when they will hit the substrate material, they will induce some of the damages, and those damages are harmful for VLSI process, because in the subsequent process, if there is a damage inside the wafer, so that damage will deteriorate the device properties. So that's why how to reduce the damage, and that damage when it is mainly coming from the plasma, that is a major concern nowadays in VLSI dry processing. Okay, there are obviously certain parameters which we can control, so that the acceleration is not very high and damages will be minimum. That all those issues I will discuss one by one in future slides. Now, DC plasma, how it is created, I described in earlier class also, but in a nutshell I can explain again. So here a vacuum chamber is there, which is known as a plasma chamber, two electrodes, and these two electrodes are separated, a wide gap is maintained, and one electrode is connected with positive of the power supply, and another electrode is connected in the negative of the power supply. So one is anode, another is cathode. Now after evacuating the chamber, you now introduce some gas whose plasma we want to create. For example, if you introduce some argon atoms, so argon plasma. If you introduce some oxygen atom, the oxygen plasma will be created. If you introduce freon gas, CF4, so that plasma will be created. What will happen if you apply certain voltage in between the electrodes? So then the gas which you introduced, and that is in a very low pressure, and that gas will be ionized. How it is ionized, how the ionization starts, that is from the photoionization or field emission. Because if you apply high electric field in between the electrodes, then because of the high field from the gas, some of the electrons will come out, and that is known as the field emission because of the high field, and those few electrons will be accelerated, because electrons are lightly very lightweight, and it is negatively charged. So automatically it will accelerate towards positively charged electrode, which is the anode. So it moves towards the anode. So as it moves faster towards the anode, So, at the anode a potential will be developed which is negatively charged, and they will further prevent acceleration of electrons towards the anode, because in the anode side a positively charged cloud will be created, and that cloud will repel further electrons to reach at this particular electrode. So, as a result of which here the electron movement after some time will be less, and then the excitation of the gas will not be there, a charged cloud will be created, and because of no excitation then you will not find any glow. And in the middle of the chamber where the ionization takes place, it may so happen some of the gas atoms or some of the electrons will be excited to a higher energy states, and then when it will come back to the original state or due to the recombination some will be ionized and again recombination will take place. So, because of the recombination then extra energy will be released, and that extra energy you can see as an emission. So, that glow is the because this is the origin of the glow inside the plasma. That means, when it is excited you can see the glow, when no excitation no glow. So, since here the charge positive charge cloud is there, so that means their electron acceleration will not be there. So, because of that there will be not no glow in this particular region, and that is known as the dark space. And since it is near the anode, it is known as anode sheath or anode dark space. Similarly, at the cathode side what will happen, since it is negatively charged, so that means here the positive ions will be accelerated, and since positively ions will be accelerated in this side and positively ions are heavier than electrons. So, then also since these are heavier, very less number of ions will reach at this particular electrode, and there even you will get the electron concentration is very low, because excitation is taking place because of the accelerating electrons, because electrons will be accelerated much more compared to the ions because of that mobility difference, and which is coming because of the difference in masses. So, here even there will not be any excitation. So, you will have a dark space which is known as cathode sheath. In this way cathode sheath and anode sheath will be created, and in this plasma since this ionization is there and a current will flow from cathode to anode, these two electrodes, and because these two electrodes are in conductor in DC plasma excitation, these are basically conductors, both cathodes and anodes, and so current will flow which is known as plasma current. Okay, the movement of the charge will be there, ions or electrons whatever movement, so that will constitute a current which is known as the plasma current. Now, on the other hand, if it happens that both the electrodes either cathode or anode, if it is a covered by some insulating film, insulating material, then what will happen, there is no direct current between these two electrodes. The current between the plasma current will immediately stop, okay, because current is terminating, because these two electrodes is supply, and through the plasma region the current path is like this. So, if these electrodes are covered by insulating film, so that means plasma current will stop, and gradually we will find the ionization will decay, and because of that reason we will find after some time the plasma extinguishes, no plasma. Okay. So, here we have to maintain a low pressure. So, if we pressure inside the chamber is more, that means gas pressure is more. So, more ionization, the glow will be more, and then obviously damage will be more. If the pressure inside the chamber is more high, what pressure? That is the gas pressure. The gas which is ionized under the influence of electric field, that pressure is more, then automatically you can expect plasma density will be more, because more and more excitation, and because of the higher density of plasma it will create more damages on the silicon wafers. Okay. And wafers are kept at one of the cathode, okay, where or anode some electrodes, because both are possible, you can place on the cathode or anode, and accordingly the species, if ions has to be accelerated then it has to be placed on cathode, isn't it? The ions are positively charged, they will move towards the cathode. So, wafers has to be put on the cathode. So, then it will reaction will take place with the surface, and you will some of the silicon or silicon dioxide surface reaction with the plasma, it will be etched. Okay. So, this is the basic mechanism of creation of plasma inside a DC glow discharge tube. Okay. Now, let us see some of the important points of the DC plasma excitation. Those are namely the what I mentioned. Sheaths are formed at the cathode and anode due to much higher speeds of the electrons caused by the low mass. That is the main reason of forming the sheaths or dark press, which is known as cathode sheath or anode sheath. The main reason is difference of mass between the electrons and ions. And there are different reaction takes place in the inside the plasma chamber, and those are ionization, dissociation, and dissociative attachment. First reaction is the ionization, where electron and the gas molecule, which is represented as A, and that will react and A will be ionized. So, when A is ionized, another extra electron will be created, and that electron and this electron becomes 2 electron. Okay. This electron hits the gas molecule and A plus ion is formed and 2 electrons are created, and those 2 electrons again accelerate, that will hit other 2 ions. And the second reaction is known as dissociation. Here AB is a gas molecule. For example, if I want a carbon dioxide plasma, carbon dioxide CO2, carbon and oxygen molecules are there, and that is represented here as AB. For freon gas, whose formula is CF4, carbon and fluorine is there. So, see there what happens in this type of dissociation, when electron hits on the atom AB. So, then what is happening? So, electron is there and A, B are separated out. There A, B are not ionized, but they are separated as individual entity. For example, in carbon dioxide or CF4, if the carbon and oxygen are separated without forming an ion, or the CF4 carbon and fluorine are separated without ionization, then this is known as the dissociation reaction. The third one is the not only dissociation, then individual species is ionized again. This is known as dissociative attachment. That means the electron hits AB, A minus and B plus is formed along with the electrons. That means here 2 ions, one is positive ion which is B plus, another is negative ion which is A minus. Both are created along with the electrons. Okay? So, these are the excitation reactions. On the other hand, it is also happening inside the plasma chamber that charge particle will be lost due to recombination. You cannot prevent it, because some of the ions will hit on the surface, or some of the ion again recombine with electrons and it will become neutral. For example, that is A minus B plus, they will recombine together, that is known as ion-ion recombination, and they will can form A and B individual entity, but no ionization. Okay. And another reaction is known as electron ion recombination, which is E minus plus A plus can give you A non ionized molecule. Okay. So, that is there, that is the reaction in DC plasma. Now, we will explain the AC plasma excitation. The AC plasma excitation chamber is like that. The difference between DC plasma excitation and AC is that the main is power supply is AC, it is not DC. In case of DC plasma excitation, cathode and anode electrodes are fixed, they are not changing. But in case of AC excitation, you are using an RF supply. So, since this is RF supply means AC, so there a particular electrode, sometimes it will be cathode and next time it may be anode, because some in the cycle chain in AC, positive half cycle, negative half cycle. So, sometimes this electrode, this one is electrode and another is whole the chamber is grounded. So, that is known as the grounded anode. The picture you see in this diagram is the grounded anode AC plasma reaction chamber. That means here anode is the ground, this is the ground symbol, and electrode is the cathode, is the RF cathode, which is the basically electrode. And this particular cathode with time is not always negatively charged. Sometimes it will negative, sometimes it is positive, because you are applying the AC signal there. And along with that, some another arrangement is connected, which is known as a matching network. In the matching network, you can find one inductance, one capacitance CM are there. This capacitance and inductance together, they will match, so that the all RF power feeds completely to the electrode. There is no reflection. And another capacitance is connected, which is a CB, and that is known as a blocking capacitance, so that the charge which is deposited or accumulated on the electrode may not dissipate through this path, because if no capacitance are there, there is a chance of this charge deposited, charge accumulated on the RF cathode, they may dissipate. Since capacitance is there, they will be prevented. Okay. Now, let us see how the reaction takes place in case of AC plasma excitation, because here there is no fixed electrode, is not never it is it will be sometimes positive and sometimes negative. So now, for example, if the this particular electrode which is mentioned here is RF cathode is, say example, it is positive. So if it is a positive, then what will happen? The electrons will be accelerated towards the positive. So all the electrons will accumulate near this electrode, and they will form a space charge, which is negative space charge, and that will prevent further acceleration of electrons towards this particular electrode cathode, because electrons are light and their mobility is high. So they will accelerate towards this electrode and they will form a cloud. And since the excitation electrons are not available there, so there is no excitation, so dark the seed, the cathode seed or whatever you say, dark space will be created there. Okay. And next cycle, because the AC, next cycle instead of positive, this will be negative. So negative means what will happen? The electrons will be repelled and ions will be accelerated towards it. But at the same time, you see the ions are heavy. So not much number of ions will terminate at this particular electrode. So if the time period is very small, that means for high frequency time period is small, so the change of the positive to electrode, positive to negative and negative to positive, that is very small. Within that small time, if the accumulated charge, negative charge, is not completely removed, so then it cannot be positive, isn't it? No, because ions which are accelerated towards this electrode in the negative half cycle, so if those are not sufficient in number, then what will happen? Then whatever the electron clouds formed in this particular space, that will not be precipitated, and that happens actually, because ions are heavy and the movement of the ions towards this particular electrode is not to that extent that net charge or net charge accumulation is possible. It will remain sometimes negative, because electron earlier cycle electrons, lot of electrons accumulated there. So because of those reasons, so you will find in this particular electrode remains similar to the cathode in DC plasma. That is why this particular electrode name is given cathode. And you can put here the substrates on the top of the cathode surface, so that because of the reaction or ions whatever it is coming towards that surface of the substrate, so it will be etched away, material will be etched, isn't it? So but since in the grounded in the seed, we have seen earlier also the cathode and anode, both seeds will be created. Here also, since the ground is the anode, because the whole chamber is the ground, So, that means the anode area will be large compared to the cathode area. Cathode is only this small electrode is the cathode, and whole chamber is the anode. Here the this diagram below this plasma excitation schematic chamber, you can here see the plot of the potential versus distance. Say, since this is grounded, this is the point VA. VA is the anode potential. The anode is grounded, is 0. Okay. So now next from this point is 0. Next coming here the plasma. So there is a plasma potential will be there, which is Vp. After that, here you see near the cathode the space charge will be negative. So the cathode potential either in the positive if you use AC, so either the positive cycle or negative cycle, in both cases it will be effectively negative. So that means that is the Vc. This is the negative potential at the RF cathode. So a relation, the ratio of Vc by Va is basically depends on the ratio of anode area to cathode area. Okay. Now you see, since anode area is a large compared to cathode area, Vc, that means the potential at the cathode will be extremely high. You say it is to the power 4. So at the cathode we found the plasma potential is very high, and that plasma potential at the cathode will help you the this reactions with the substrate materials, and the efficiency of reaction also depends on the plasma power and this particular plasma potential which is available near the cathode. Okay. So now next let us see what are the specific features of this RF plasma. A RF signal which is in the range of megahertz, so that means their change of the electrode positive to negative is very fast, because in the megahertz range the RF signal you are using is applied to an electrode through an impedance matching network. An impedance matching network in all RF power supply is provided so that the power properly feeds to the electrode. Response of the plasma to the positive and negative cycles are different, and just now I explained the behavior of the plasma in the negative cycle as well as in the positive cycle. As light electrons are highly mobile and heavy ions are less mobile, a negative charge builds on the electrode, provided a blocking capacitor Cb prevents discharge. In the earlier diagram I showed you the Cb, that is the blocking capacitor, that will prevent discharge of the negative charge which is accumulated on the electrode, cathode electrode. RF source causes more efficient ionization in discharge than DC fields. If plasma and that RF source 13.56 megahertz is used, if plasma sustains at a minimum operating pressure, RF plasma sustains at a minimum operating pressure of 0.5 Pascal, while DC plasma requires 9 Pascal. So this particular point is very important. Because of that reason, RF plasma is much more popular than DC in VLSI dry processing. The main advantages of RF plasma are there, even very low pressure, operating pressure 0.5 Pascal only, even that very low operating pressure, the efficient ionization will take place inside the plasma chamber, and if ionization is efficient much, then what will happen? The etching will be much more efficient, etch rate will be high also. All those things, all these better things is observed in RF plasma etching. And the plasma source uses 13.56 megahertz RF signal. Okay. And that 13.56 megahertz has taken as a standard frequency for most RF plasma chambers, plasma sources. Next, we will discuss now the basic etching behavior, and that is the fluorocarbon chemistry, how the etching takes place in plasma chamber with silicon and silicon dioxide. Now, the dry etch means we are not using any liquid substance to etch either silicon or silicon dioxide. We use some gas, and in this particular example we are using this CF4, which is known as a freon gas, and this freon, it reacts with electron. When it is bombarded with electron, CF3 plus will be created along with fluorine atom and 2 electrons. When electron is bombarded on the freon gas, which is CF4, then fragment, molecular fragment, which is CF3, will be created along with a fluorine atom and 2 electrons. This atomic fluorine is an active agent for both silicon and silicon dioxide by the formation of volatile SiF4 and oxygen. In a dry processing, I already mentioned earlier that when it reacts with the etch material, then the byproduct should be volatile. If it is not volatile, then it will deposit on the substrate and it will further stops the etching process. In this particular reaction, fluorocarbon reaction, we found that CF4 means freon gas, it reacts with silicon and silicon dioxide and it will form volatile, which is SiF4, and at the same time oxygen. And SiF4 and oxygen both are gaseous, and it is ejected from the plasma chamber through the vacuum suction. In this particular reaction, you can see that the reaction taking place with silicon and silicon dioxide, that is not freon itself but fluorine atom. That means more and more fluorine atoms are available, then you will get more and more etching. Etching will be much more efficient. In that respect, we have to increase fluorine. But one problem is there, when CF3 plus and fluorine is created, at the same time the reverse reaction will also take place, and the CF3 plus and fluorine, they will recombine and form the CF4. That means by any way, if we can reduce the CF4 or this carbon molecule in this particular composition, then we can get more fluorine atom rather CF3. So using certain technique, the etching efficiency is improved, and that technique is introduction of some oxygen into the chamber. Instead of CF4 itself, now if we introduce CF4 plus oxygen, so then CF4 plus oxygen plasma will help you efficient dry etch rate, or it will be improved. Now in this particular case, we can see etch rate of silicon increases if certain amount of oxygen is added to CF4. How? Because this extra oxygen, they will form CO, CO2 and COF4, and they will increase the fluorine atom concentration in the chamber. And it has been observed experimentally that the maximum etch rate of silicon has been observed when the oxygen concentration is nearly 12%. At the same time, maximum etch rate of silicon dioxide has been observed when etch rate is when the oxygen concentration is 20%. And in oxidizing ambient, that means if we use CF4 and oxygen plasma, then the reaction is CF4 plus SiO2, which gives SiF4 which is volatile, and at the same time CO, CO2 and COF4 all are volatile, isn't it? Now, one point you can observe in this reaction that the CF4 plasma etches both silicon and silicon dioxide. That means etch selectivity you are not getting. How to increase the etch selectivity? So, there instead of CF4 and oxygen plasma, you can use CF4 plus hydrogen plasma. So, if you use hydrogen plasma, then what will happen? The fluorine and hydrogen, they will combine together and they will form HF. So, in that particular reaction, we will find that the etching of silicon dioxide will remain intact, but etching of silicon will low down, okay, will be lower. So, because of that hydrogen introduction, we can maintain the etch rate of oxide same, but silicon less. So, selectivity will be improved, because if you want to etch only silicon dioxide, then you go for CF4 and hydrogen plasma. Okay. So, these are the some techniques which you can utilize to increase the selectivity, and efficiency can be improved by changing the concentration of the gas composition. Okay. Now, if you compare this dry etch reaction along with the wet etch, then reactions are shown below, and they are silicon dioxide and 6 HF, means you are there, you are using hydrofluoric acid, that is liquid etcher. If you use hydrofluoric acid, then H2SiF6 and H2O, and this H2SiF6 again dissociates into SiF4 and twice HF. So, this HF is liquid there along with H2O and SiF4, and that is volatile. That is, both in wet etching and dry etching, you can see the etch product should be either volatile, so that you can remove it through gas exhaust, or it should be another liquid which is dissolvable in water, another composition which is dissolved in water, so that the etch composition will not, that means etch product will not attack the silicon surface. At the same time, in wet etch process, the problem is, if the hydrofluoric acid consumption, you see 6 atoms and ultimately end up with 2 HF, that means its concentration reduces. So, the H rod will obviously lower if you etch for a longer time, isn't it? That is not true in case of dry etching process, because there the gas through the inlet, you are continuously pouring the gases, and through the outlet the gas is taken out. So, a continuous flow is maintained into the chamber. So, always the wafer faces a fresh gas. Okay. And in wet etching, on the other hand, you are getting the etch byproduct can dilute the gas molecules. So, that is one of the difference in wet and dry etch process. Next, we will discuss on plasma etch parameters. What are the different parameters which affect the etching process? Those are namely excitation frequency. I am considering the RF plasma etching. The excitation frequency affects production rate of reactive radicals and level of plasma seed potential at the wafer surface. If the frequency change, that is why a standard frequency 13.56 megahertz is used in case of RF plasma. Second is high seed potential. If the in RF plasma we use the megahertz range RF signal. If the frequency is more, then high seed potential, H rate is high, and high anisotropic H we can observe. If we increase the frequency into the microwave region, that is 10 to the power 9 hertz, that is gigahertz range, then low seed potential has been observed, H rate is low, and H is isotropic in nature. That is the difference in RF and microwave plasma. That if we increase the frequency, the seed potential becomes lower, H rate is again lower, and the etching is isotropic if you increase the frequency of the plasma. So, these are the excitation frequency parameter and its effect on the plasma properties, etching properties. Next is the flow rate, because when you are creating plasma, you are introducing some gases, and that gas may be the argon or maybe freon, maybe oxygen, maybe hydrogen, etc. The flow rate is an important parameter in dynamic environment of feed gases into the system. The flow rate gives you a residence time, that means how long the gas molecules will stay inside the plasma chamber, and that residence time is given by PV by R, where P is the pressure in torr and V is the volume of process chamber in liters, and R is the flow rate of feed gas in torr liters per second. So, if the residence time is more, so then obviously you can see that reaction will be longer time, excitation will be longer, and its effect will be there in H rate. Normal flow rate of feed gas in plasma chamber is about 79 SCCM, and SCCM is a unit which is used for the flow rate, and its full name is standard cubic centimeter per minute, and that is normally from cylinder you can get torr, the cylinder pressure of the H gas, and torr liters per second to the SCCM, the conversion rate is 1 torr liter per second is equal to 79 SCCM. This is the conversion rate. In the flow rate in many plasma reactors is expressed in terms of the standard cubic centimeter per minute. SCCM is a common unit which is used in standard etching system. Okay. So, the flow rate is one H parameter. Next is, because flow rate decides the residence time of the plasma inside the chamber, and it depends on the PV by R. Next parameter is the pressure. Keeping all other parameter constant, H rate generally increases with increased pressure in the 5 to 50 millitorr range. This may be due to increase in residence time, because residence time relation you have seen, that is PV by R. So, that residence time is directly related to P. So, if you increase the pressure in the range of 5 to 50 millitorr, then it is observed the H rate increases. That is the effect of pressure, means plasma pressure on H rate. Next, seed potential decreases with increasing power, that leads to slow isotropic etch. Seed potential, that is electrode seed, and the another seed will be formed in the chamber with plasma, that decreases with increasing power, and which basically leads to slow isotropic etch. High pressure decreases ion energy due to frequent collisions as a result of low mean free path. That is another point you have to consider. If you increase the pressure, what will happen? The collision between the ions will be more if you increase the pressure, and their mean free path will be less. Because of that frequent collision and mean free path will be less, so it will decrease the ion energy, because you are interested how many ions are reaching on the silicon or silicon dioxide surface which is the substrate surface basically, and that substrate is kept on the electrode cathode. So, there high pressure may decrease ion energy because of lot of collision inside the plasma chamber. The fourth point is the power. Increasing RF power increases the sheath potential, and it also increases concentrations of the reactive ion and neutral ions, and etch rate increases almost linearly with power. If you increase power, it will increase sheath potential, which increases the concentrations of the reactive ion and neutral atoms. Sorry, etch rate increases almost linearly with power. Fifth point is magnetic confinement. In some of the plasma chamber, a magnetic field is used to confine the plasma. Because plasma are the charged particles, plasma contains ions and electrons and neutrals particles also. So, those combination of ions and neutron particles that phase, the whole plasma can be confined into the chamber by using magnetic field, because magnetic field will interact with charged particles, and that will help confinement of the plasma on the substrate surface, and the etch rate will be more. Okay? That magnetic field behind the etching wafer leads to higher plasma densities and higher etch rates. Non-uniform magnetic field also leads to non-uniform etch rate. So, that is why when you are using the magnetic confinement method, then you have to ensure that magnetic field should be uniform over the entire surface. Otherwise, non-uniform magnetic field will lead to non-uniform plasma power, plasma etch will be non-uniform. Okay. So, these are all the parameters which will decide the etch characteristics of the plasma etch system. Now, another point we will discuss, that is known as sputter etch. Now, in all plasma process, you will find the material is etched because of two reasons. One is purely physical and other is chemical. So, as I have already discussed that silicon reacts with fluorine, it is forming SiF4, that is a chemical reaction, chemical process, and some etch product is there which is volatile in nature. On the other hand, in the plasma, if ions are there and electrons are there, and those ions, if you keep the substrate on the cathode, then obviously the ions will be accelerated towards the cathode, and those ions will hit the cathode material, and that is the physical reaction. So, because of high momentum, because ions are heavy particles, and those heavy ions will hit the substrate surface, and from there some of the materials will come out, and that is purely physical process. No chemical reaction will take place in this method, and that is known as sputter etch. Sputter etch is completely physical process, and the sputtering is the ejection of material from a surface caused by bombardment of energetic inert ions like argon and xenon. Okay? Interaction is purely physical, and one parameter which is often considered, we talk about, that is the sputter yield in a sputter etch process. Sputter yield is defined as the number of ejected surface atoms per incoming ion at a given ion energy. That means one electron is hitting or one ion is hitting on the surface, and how many atoms are coming out from the surface per unit incoming atom. So, that is known as sputter yield, that is expressed in percentage. So, you can always have that particular value by just multiplying 100. Okay. The ratio is multiplied by 100, you will get this sputter yield. Yield change with angle of ion flux, obviously, because if the ions are incident on the surface at a particular angle, not incident normal angle, so then the yield will also change. Okay. Then the yield process depends, the sputtered yield of a particular plasma system depends on the angle of incidence of the ions with the substrate surface. Ion bombardment contributes damage. That is another point which we also remember, because this is a physical process, and in this physical process, if the ions are bombarded with higher energy, it will damage the surface. That is why pure sputter etch or physical etching process is avoided in VLSI technology. Now, I can show you a diagram of the plasma chamber, and you can see here. So, this is the anode and cathode, and here a RF frequency generator, RF power is applied, a tuning network which will help you to match the RF power to the cathode, and the blocking capacitor C is there, and gas inlet is through this path, and anode is grounded and is a pumping out. This is a basically actual chamber of the RF sputter etching. So, you can keep the wafers on the cathode, those are kept here. Okay. And now, since their cathode is, the ions will be accelerated towards the cathode, and it will physically bombard on the surface of the silicon wafer, and some of the material from the surface of the silicon material will come out, and etching process continues with this. This is the very simple structure of sputter etch process or a sputter etching system. Okay. So, the plasma process, or this is also a plasma process, or sputtered one is purely physical, and there are some process where we use both physical as well as the chemical process, because where the fluorine and silicon dioxide reacts and form SiF4. So, there you cannot say that there is no physical bombardment. So, there also the ions will bombard on the surface of the silicon or silicon dioxide, and some material will come. That is a combination of both physical and chemical process. Okay. So, here also you have the H, the sputter H parameters will depend on the pressure inside the chamber. Pressure means the gas flow rate, basic pressure, base pressure of the plasma chamber, RF power, RF frequency, all those parameters are also valid in this particular sputter etch system to decide the etch rate, sputter etch rate. And the sputtering also, the sputter etch rate is sometimes used for cleaning the silicon wafer before actual etching process starts. Sputtered etch is sometimes used for cleaning silicon wafers. Okay. So, let me stop here. In the next lecture, I will start discussion on different etch systems.